Okay, welcome to the third video. This is really where the discrete random variable stuff kicks off. Feel free to pause the video now and have a go at the questions. Okay, how many 3s would you expect? Probability of getting a 3 is 1/6, so you'd expect to get 3s roughly 1/6 of the time. So that is 20. Now, let's be clear, you wouldn't always get 20. In fact, pretty likely you get 19 or 21 or something. And if somebody said to you, I got exactly 23s every single time, you might be a bit suspicious. What would you expect the average score to be? Well, you would expect roughly 21s, 22s, 23s, plus, I'm getting my pluses and my multiplications muddled here. So I'm calculating what I would expect the total of all the scores to be. 20 lots of 2, 20 lots of 3, 20 lots of 4, 20 lots of 5 and 20 lots of 6, and then you divide that by the total number of rolls. Now, I'm going to rewrite that, not in perhaps the most direct way of calculating it, but in a way that's going to be relevant later. I'm going to split this fraction up, and I'm going to write it as, well, 20 over 120 times 1, etc., etc. Let me do a few more of those etceteras. Plus 20 over 120 times 2, and so on, all the way down to 20 over 120 times 6. And then I'm actually going to simplify those fractions. So this is a slightly different way of thinking about the mean of a load of numbers. You get 1/6 of 1, plus 1/6 of 2, plus 1/6 of 3, plus 1/6 of 6. Okay, so you multiply the numbers by the proportion of the total numbers, which are those things. So 1/6 of the numbers are 1, so we multiply 1 by a 6th. Okay, that gives you 1/6 of 1 plus 2 plus 3 plus 4 plus 5 plus 6. You could use the sum of an arithmetic progression to sum that if you wanted, but it's actually just, probably quicker to just write it, it's actually just 21. So you 21 over 6, which is dividing top and bottom by 3, 7 over 2, 3.5 for the expected value. So now we come to part C of this question. If the average score out of 120 rolls were 4.1, would you be suspicious? So 4.1 is a little bit more than what we would expect. We would expect 7 over 2, which is 3.5 as a decimal. So yeah, that's a bit high actually. You're thinking about a lot of 6s and 5s and 4s and not nearly so many 1s and 2s and 3s. But I don't think I would be that suspicious. We'll talk a little bit more about that later, but the reason I wouldn't be that suspicious is that somehow there are only 120 rolls. So although I expect roughly 20 of each, I'm not too surprised if there's 23 5s and 22 6s, and that might already be enough to drag the average up like that. Okay, so not too suspicious. But part D, 120,000 dice rolled. What would you expect the average score to be? Well, I hope we can see you'd expect not 20 of each number, but 20,000 of each number. Okay, so let me just rub out. We can probably do better than that. Delete that stuff. So you would expect 20,000 times 1 plus all the way up to 20,000 times 6, and then you divide all of that stuff by 120,000. Again, you wouldn't guarantee exactly 20,000 ones, but roughly that many. And then I hope you can see if you split the fraction up as 20,000 times 1 over 120,000, 20,000 times 2 over 120,000, and so on, you would actually get exactly the same expression as we did here. So you would still expect, maybe this is not surprising, that the average score would be 3.5. It's actually the average of the possible values on the die. However, the point about this is that if you roll 120,000 times, and someone says to you the average is not 3.5, it's actually 4.1, so more than half a point above what you expected. At this point, I think I'm beginning to get suspicious, because although I wouldn't be terribly surprised if I got, in the first case, 120 rolls, if I got 24 6s, if I roll at 120,000 times and I get 24,000 6s, 4,000 more than what I would have expected, then I'm beginning to get suspicious. So I think the answer to that is probably just yes. When we come on to talking about hypothesis testing, maybe next year, you'll be able to answer that question a bit more accurately.